Okay, welcome back to Note Set 12. So this is Note Set 12 Part B. I'm breaking this into two videos, but I'll keep the note set as one on the website. So just as before, we are still in section 5.4 of the textbook, and we were talking about various aspects of discrete time filters. So we just finished looking at low pass to high pass transformations. And now we'll use this idea of pole zero placement, not the transformation part, but just the idea of placing poles and zeros, to design a few particular types of filters that are not low pass or high pass, but are kind of interesting nonetheless. So the first one is a digital resonator, and the textbook, I think, alludes to a few applications of this, but basically it's a filter that has a very high and sharp resonant peak. And so it's a particular type of bandpass filter with a very narrow pass band and not particularly flat. So we're going to create a resonant peak, one at positive frequency, one at the negative of that particular frequency. And we'll see that the angle of the pole, and these are ideas that you should know from earlier studies, but the angle of the pole position will control the frequency at which we see the resonant peak, and the radius of the pole position will determine how pronounced that peak is, how sharp. And we'll also have two zeros, and we can place those wherever we really desire. Desired. So that should be desired. Sorry about that. But common places to put them are put them both at the origin, and an even better place is to put one at omega equal to 0 and one at the omega equal to plus or minus pi. So that's z equal to 1 and z equal to minus 1. So given that, we can quickly figure out what our transfer function looks like. So here are our two poles at position r, radius r, and angle plus or minus omega 0. So you should be able to verify and convince yourself that those two factors give us that. And this is in the z inverse form, so if we multiplied by z squared over z squared, we would clear the z inverses, and it's this z squared in the numerator that gives us two zeros at the origin. Okay, so we've got that set up, and then the other setup has exactly the same denominator as before, and then we put in the zeros where we want, one at plus 1 and one at minus 1. And if you multiply top and bottom by z squared, you'll see that the zeros are where we would expect. A little easier to see it that way. So in both cases, if we multiply the denominator factors together, we get the second order polynomial and z inverse in the bottom that tells us what the difference equation would look like. On the one on the left, we put a B0 up there, and that allows us to adjust up and down the whole structure. Likewise, we have a G over here for kind of a DC gain that allows us to adjust the up and down structure however we want. So we can pick those separately to put the height at whatever value we want. Okay, so those are the basic structures, and we've just arrived at those kind of by thinking about where we want poles, where we want zeros, and we can figure out what our transfer function looks like. We can then figure out what our difference equation looks like, and from that you can actually get the block diagram. You can then build this in hardware, build it in software, whatever you want. So looking at the case with the zeros at the origin, we can start with this transfer function that we saw on the previous page. We have a nice pole zero diagram here showing the poles at radius r and at angles of omega 0 and negative omega 0, with two zeros at the origin. A little hard to tell that there's two there, but there are. And if we were to plot this, we could use MATLAB to plot this. And it's been plotted here, magnitude and phase for two different values of r. And you can see that as r goes closer to 1, in other words, as the pole moves closer to the unit circle, we see that we get a sharper characteristic on the resonant peaks, and we also get things pushed down more in the regions away from the resonant peaks. And the actual frequency at where the resonant peak occurs, you can actually derive, and the book shows for this case, that the resonant frequency is related to the pole frequency through this equation. And if you explore this, plug in different values of r and different values of omega 0 and see what the resulting omega sub r is, you can see that as r gets closer to 1, we get closer to this just being omega sub r being equal to omega 0. In fact, if you look at this structure here, as r goes to 1, we end up with a 1 plus 1 in the numerator, so that's 2, and in the denominator we have 2 times 1, which is 2, so we end up with 2 over 2. So this term goes to 1, and we see that we have inverse cosine of omega 0. So as r gets closer to the unit circle, omega sub r becomes closer to omega 0. And then this also gives us a measure of the width, the 3 dB bandwidth of the peak, and we can see that as r gets closer to 1, the width gets narrower and narrower and narrower, and in fact in the limit goes to 0. So those are very interesting things to think about, and we basically could puzzle those things out roughly anyway from things that we saw in the signals and systems class, and here we're seeing an explicit application of those ideas. To look at the resonator with zeros at z equal to plus or minus 1, we get something that looks like this, and we see the main difference here is that we can tie it right down to 0. It's been a while since I made these notes, and I don't remember if there was a expression for the position of the resonant peak. I suspect that the position of the resonant frequency is the same as before, but I don't know about the bandwidth result, but they should be similar anyway. Okay, so let's go on to the next slide here. If we think about what we just built, a resonator, and we think about moving that pole onto the unit circle, letting r be equal to 1, and we think about the inverse transform of this thing, we can show that it ends up looking like this. We can see that for r less than 1, this thing is going to decay as it oscillates. But if we let r be equal to 1, then this term out in front with the r no longer decays and in fact stays constant. So when r is equal to 1, we just have a constant times a sine wave of a specific frequency, omega sub 0. So if we put the pole on the unit circle, this thing actually acts like a discrete time oscillator. So it's a very nice way of actually generating a sinusoid without having to actually sit there and compute these things. We could just create an n vector, just keep incrementing our n, multiply n times omega 0, and compute sine of it or cosine. But that would require actual trigonometric operations in our computer. This would be a very easy way to do that without having to actually do trigonometric computations. And so if you're interested in this, the textbook goes into this in a little bit more detail. So these are very specialized things, so I'm not really dwelling on them. I'm just making you aware of them and pointing you to where you can go if you're interested in more details. I'm much more interested in you learning the big ideas than the tiny little ideas. Now that's not to say that I won't ask a question that seems like a tiny little idea, but is asking you to apply a big idea for that. Okay, notch filters are kind of the reverse or the flip of resonators. So here we're going to put two complex conjugate zeros right on the unit circle to create a null at a desired frequency. So the angle of those zeros will tell us which frequency gets nulled out. And then we'll have two poles, and if we put both poles at the origin, then we get an FIR filter. Don't let anybody ever tell you that an FIR filter has no poles. Every FIR filter has as many poles as zeros. It's just that all the poles are at the origin. So now we've got, or we could put our poles somewhere else, depending on what other shapes we want. So if we do poles at the origin, we're just creating this product of two zeros in the z inverse form. And if you convert that into the z squared form, you get something that looks like this, and there you can see are the two poles at the origin. Likewise, we could start off with that same structure in the numerator and put two explicit poles in the denominator. And then after converting with a little bit of algebra and getting back into the z form, we get something that looks like that. So the numerator is the same as before. Our denominator now is something that's going to give us some generic poles rather than just poles at the origin. Okay, so that's transfer function for a notch filter, and then here's a plot of the frequency responses, which you can find with using MATLAB with FreqZ. So the poles at the origin one, yeah, we get some notches, but not too much interesting is happening here. If we put poles right at the same frequency that we're putting the notches, so this omega 0 is the frequency where we're putting the notches, and in this case we chose it to be pi over 4, it looks like. And then we adjust the radius of those poles. So remember, the zeros are right on the unit circle, and so what we're doing is we're putting poles right at the same angle as the zeros, and then we're moving them either in or out relative to the unit circle. And you can see that as we let the pole get close to the unit circle, we get a nicer and nicer notch filter. So we can create a fairly nice notch filter very simply doing it this way. It's a really nice response. Of course, we don't have the linear phase that we have for the FIR version of it, or the non-recursive version. And I guess I should comment here, just in passing. Notice the discontinuities in this phase, but other than those discontinuities, it's still just a bunch of lines of the same slope. So what's happening there is discontinuities at these places where the magnitude goes to 0. So we still consider this to be a linear phase response. Okay, so that's notchers. Another type of specialized filter is called comb filters. And there's a variety of different uses for these. And one of the most common uses is, suppose you have some sort of series of harmonics that you'd like to completely null out, for example. So if you can put notches at all of those frequencies, then you would get rid of this component, which is looking basically like a periodic component. So if you have a periodic component, Fourier series tells us that it's going to have frequency components spaced at integer multiples of its fundamental frequency. So there's going to be a whole bunch of different frequencies, but all harmonically related. And it'd be nice to be able to build a comb filter that could just completely wipe that out, put some nulls right at those frequencies. So a comb filter has this name because it looks like the shape of an actual physical comb. So let's start off with a very simple form. We've seen this filter before. We have, for the case of m being even, we just add up m plus 1 successive samples and divide by m plus 1. We can easily write the transfer function that way, and then with a little bit of algebra we can show that it also can be written this way. And when we do have that structure, that after we've manipulated it that way, we can see this structure here. We have zeros at those frequencies, and then we end up with a pole at z equal to 1, which corresponds to omega equal to 0. So for the k equal to 0 case, we'll have a 0 at that same frequency, and so those things cancel each other out, even though they're in there. Now, you may remember that we cautioned about relying on pole 0 cancellation. In this case, there's really no danger of that because it all comes from these coefficients being equal to 1, and we can make those coefficients identically equal to 1. We don't have to worry about any rounding issues or anything like that. The impulse response is just a rectangular function, and then we can take the DTFT of that and we can find our frequency response of that. And this thing looks like, as we'll see, looks kind of like a sinc function. It's not exactly a sinc function, but it's what I call a discrete time sinc function, and we'll see what it looks like on the next slide. So to get a feeling for what this does, let's look at the numerator of this. So this out in front is just a constant 1 over m plus 1, and then a phase shift. So let's just look at the other stuff in the brackets here. So if we look at the numerator inside the brackets, so we look at this term, it's just a sine function. And so as a function of omega, it just goes up and down, and goes through 0 at omega equal to 0. And the rate at which it goes up and down is set by m plus 1 over 2. Remember, omega here is the variable that we're plotting it against, and so anything multiplying omega is going to play the role of a frequency. I know it's weird, omega is frequency, but for the moment, just suspend that view and think of omega as x or some other variable. We now have a frequency in that variable, and that frequency will be set by m plus 1 over 2. But we also know that where it will cross and take on the value of 0. So it's whenever the argument of the sign is equal to an integer multiple of pi. And if we solve that, we can find out precisely where those frequencies are. And it's just some integer k times 2 pi divided by m plus 1. So that's what's going on in the numerator. What's going on down in the denominator here is, just clear that out. What's going on down in the denominator is this function, and we notice that because that's just omega over 2, that oscillates much slower. In fact, it just does 1/2 cycle from the range minus pi to pi. Now you remember the sinc function itself was sine over, sine x over x. So in that case, it was a, straight line for the denominator, sine x over x. X is a straight line. But in our case here, we have a sine function, and it's close to being a straight line, but not quite. So this thing looks sort of like a sinc function. It has behavior similar to a sinc function, as we see a plot here for m equal to 10, but it's not exactly like a sinc function. So anyway, we see that there are a bunch of notches, and the notches are at these frequencies, and so we have notches at harmonically related positions. And remember, we talked about a pole in the denominator canceling a 0 at omega equal to 0 in the numerator. Well, that's why we end up having something. Here's the 0 in the numerator at omega equal to 0, but yet our overall frequency response does not go to 0 at omega equal to 0. So we can see that here from L'Hopital's rule, because we end up, if we look at omega equal to 0, we have 0 over 0, so we can apply L'Hopital's rule and find that it's equal to 1. Or we can see it in the z domain with that pole 0 cancellation. So there's a simple comb filter. Those do show up now and then. And here's a more general approach to design a comb filter. Suppose we don't really want that. We got the nulls that we wanted, but the response outside of where the nulls were was, not terribly good for a lot of applications. So suppose we start with some FIR filter, and we can design that to have, some achievable shape that's desired. And then what we're going to do is replace z here by z to the L, where L is some positive integer. So now we get something that looks like that. And if we now convert that into its equivalent frequency response, we can find out that it's related to the original frequency response by just replacing omega by L omega. And so when we, since L is a positive integer, this is actually taking h of omega and scrunching it in by a factor of L. So to illustrate, suppose this is our original h of omega. After we've replaced z by z to the L, we get a new function, a new filter that will look like this. So notice that from minus pi to pi, it's this thing scrunched in. And so the triangles are narrower, and we get a bunch coming in from that were outside. They were the spectral replicas out here before. Okay, so I illustrate this with this nice triangle, even though we can't really get that from an FIR filter, but it sure is convenient for doing that kind of stuff. Okay, so let's see, we got a few more slides here. Continuing in this development, we'd like to explore what this, there we go again, I did that last night and I'm doing it again. We're going to explore what this change of z to the L does. um, and see how we would actually implement this filter. So we've only seen that making that change gives us a frequency response that does in fact give us a nice um, comb filter, but we've not seen how we would actually build that. So suppose we have some original h of k, and we now can say that since we're replacing z by z to the L, we can write the z transform of that like that. And so that is just h of 0, h of 1 times z to the minus L, h of 2 times z to the minus 2L. Now look at what we have here. We really got a z transform, but we're missing the z to the minus 1, z to the minus 2, z to the minus 3, and so on, assuming L is a fairly sizable integer. But we're missing all those terms. So if we stick them in, here they are. We've now inserted those into the function. I'll clear this away, and I'll remember to go back to my pen so I don't move the whole slide around. So we insert a bunch of zeros here, we insert a bunch of zeros there, and so that is the new impulse response. So the impulse response of the filter that is H sub capital L is just one that has one original sample, then L zeros inserted, then the next one, then L zeros. And I'm starting to doubt myself here whether it is, no, I think it's L minus 1 zeros. So it should be L minus 1 zeros in both cases. And we can see that, right? Because we're going, it's z to the minus 1, z to the minus 2, all the way out to z to the minus L minus 1. So if we count those, we've got 1, 2, all the way out to L minus 1. So it's L minus 1 zeros that are inserted. So here is a case, this would be actually L equal to 4, because I'm putting in 3 zeros. So this is how we would implement in a block diagram, and that block diagram could drive how we write code or how we build hardware to do this. So you should be able to convince yourself that this block diagram does indeed follow from that impulse response. So if we applied this to the uniform weight FIR filter that we had before, we could get something that looks like this. And this would be our frequency response, and this would be the comb filter that would result. And the book has a nice discussion that I'm not going into it, but it shows how a comb filter can be used to separate solar harmonics from lunar harmonics in ionospheric measurements. So it's kind of a cool application of a comb filter. So you might want to take a look at that to get a feeling for how these things actually play out in the real world. And we'll close things off here with all pass filters. And as I already said at the beginning of the first part of this video, 12A, why would we want an all pass filter? Well, one reason is to accomplish some sort of phase equalization. They are also used for separating signals that have been multiplexed. And I have a nice little project that I'll assign once we get underway with the MATLAB that will show you how these things are applied. We'll get that up and running in a little while. So suppose we have some real valued coefficients. We create some polynomial. Technically, it's a polynomial in z inverse. And so we call that a of z. And then we form a transfer function that is a of z in the denominator and a of z inverse in the numerator. So if we do that, and then we put a z to the minus n out in front. So if we do that, and then take the magnitude of this, look at the magnitude squared. So we want to look at the magnitude squared of the thing that we just created. And you should be able to convince yourself and verify that finding the magnitude squared of the frequency response can be done by taking the transfer function, multiplying it by the transfer function as a function of z inverse, and then evaluating on the unit circle. So that operation actually gives you this. And the reason that we find it this way is that it's easier to see what actually happens. So we take the transfer function, so this thing goes directly into here. So we get a z inverse divided by a of z with a z to the minus n. Then we're going to take this thing with z replaced by z inverse. So we then have an a of z in the numerator. We'll have an a of z inverse in the denominator. And instead of having z to the minus n, we'll have z to the n. So let me clear all this stuff out here. So then we can see that we've got an a to the z inverse in the numerator and an a to the z inverse in the denominator, and so those cancel. Likewise, an a of z cancels, and likewise a z to the minus n times a z to the n cancels. Everything cancels, so we're left with 1 for all. That was a pretty crappy for all. So the mathematical symbol is an upside down A for all omega. So as long as we form the filter, the original filter like this, regardless of the values of the a sub k's, we'll always get an all-pass filter if we form our overall transfer function this way. So that means we're free to pick any set of a sub k's, and we would pick those to achieve whatever phase function is desirable and still achievable with this form. The last slide here just looks at the pole zero locations. So for the all-pass pole zero reciprocal locations, for a first order one, because of the relationship of a of z and a of z inverse, these things will form reciprocals. So if the pole is at a, the zero is at 1 over a. And then here we see for the second order all pass filter, we have 2 poles inside the unit circle. One is at r at omega 0, and the other one is radius r at minus omega 0. And the zeros are just along those lines, but they are at a distance that's the reciprocal of the radius of the poles. And so looking at this, we see that these two things give us nice building blocks, and that we can then create a more general all-pass filter by basically just cascading a bunch of stages that are either this or this. And so this would be the most generic structure that we would have for an all-pass filter. Okay, so we'll stop there. This is the end of Chapter 5. And in our next set of notes, we'll be going into some issues of sampling theory. And so we will start off with a quick review, a sort of quick review of the general sampling theory done the way that I like to do it, not the way that most books do it. So this will be pretty much the same as what you saw in Signals and Systems, but I want you to see it again so that you really know it. Then we'll go into some new things for you that talk about some more advanced concepts for sampling. All right, we'll see you in the next video.